Flutube, get it straight. Okay, let's look at some hints for homework number 4. Problem number 1 is pretty similar to the one we worked in class, so I'm going to skip right ahead to problem number 2. So here we have a two-dimensional velocity field equations given, and we want to plot the streamline through the origin, 0, 0. So here's the equation of the velocity field. So it's very simple in the u component or x direction. It's just a function of x, so u is equal to x. In the v direction, it's a little more complicated. It's a function of both x and y. We have it there. So the key to this problem is recall that the streamlines are determined by remembering that the slope of the streamline dy dx is equal to the slope of the velocity in the y component over the velocity in the x component, or v over u. So we simply put the given equations into this form, v over u, and that simplifies because the x's cancel. And now we have to separate the terms and integrate, not forgetting the constant of integration because that gives you the family of lines. But just like in calculus where you're looking for solving for that constant, you use information given, that is, that they want the streamline, the specific streamline that goes through the origin 0, 0 in order to work out the value of that constant. Okay, let's look at the next problem, problem 3, which is text problem 4.16. This is a non-steady flow case because the velocity field changes with time. But note, however, that you can consider it steady flow for each of the two time periods given because it's given as the flow field for that time period. So it's not changing within the time period. So for part A, you have two particles released at different times, both from the origin. Particle 1 leaves at time equals 0, and it feels 20 seconds of the flow field number 1. Then it switches over to flow field number 2 for the next 10 seconds. So you'll see it moving in one way for the first 20 seconds, and then in another way for 10 seconds. So you should see a particle kind of moving off in a straight line and then shifting into another straight line. Now for particle 2, it doesn't even start until t equals 20 seconds. So it just feels, only feels 10 seconds of flow field number 2. Sorry for the typo there. But it feels 10 seconds of flow field number 2. So it should just go off on one straight line. So the path lines show the path covered by that particle. So you just trace out the path it covers. Now for part B, we're looking at the streamlines, which are very related here. During a steady state situation, the streamlines are the same as the path lines, right? But there's a whole family of them. So we'll obtain them like you did with problem 2, only the integration will be very simple here. And remember, there's an infinite number of streamlines, so that means there's all different kinds of C. In problem 2, you were given a C by being told that you want to go through the origin. Here you just want to see enough of them to see the pattern. And it'll look something like this, where you have the solid lines are one of the flow fields, and the dashed lines are the other. Looks a little bit similar to this one, in fact. So let's look also at problem 5. So this is text problem 4.33, and this problem focuses on the trade-off between local and convective acceleration that we've talked about in class. Remember the local acceleration is the du dt term in this case. So we have a one-dimensional case here, so we just have the u velocity. So u with time is the local acceleration, and then u with space, which is u times du dx, is the convective acceleration for this one-dimensional problem, that is. So the total acceleration is the sum of those two components. So if what you want to do here is work out the math, it should be pretty basic as a function of u and time. So get your time term, and you'll work out the local acceleration term and the convective acceleration term. You sum those terms and try to draw the conclusions, try to answer the questions posed. It's good to think about this one. And that's it for the hints for homework number 2.